If you've made it this far in life without getting yourself addicted to nicotine, don't start now. We've known since the 1930s that smoking causes lung cancer. It was insurance company actuarials that first figured that out. I'm Professor Mark Hinders, Applied Science Department at William & Mary. So vaping is all the rage these days with kids and whatnot. Of course, vaping, where a liquid is heated to drive off the nicotine and flavoring chemicals, is safer than smoking analog cigarettes. Still, it's a nicotine delivery device. If you're of age, both of these things are legal products that are designed to deliver nicotine, and which is bad for you and addictive, but as long as you understand that going in, that's your choice. What you might not know is there's an intermediate technology between smoking analog cigarettes and the little vaping liquid devices. The in-between thing, that technology uses a cigarette, but instead of setting it on fire, it uses an electrically controlled heating element to heat, not burn the cigarette, and thereby drive off the nicotine and the flavoring compounds and so on. Still bad for you, somewhere in between vaping and analog cigarettes. The interesting part about it is that there's decades of work that has gone into developing these safer cigarettes that heat, not burn. And I know about this because we had a PhD student in the lab, Mike Watkins, and his employer sent him back to school to solve a particular technical problem with one of the early heat not burn cigarette devices. The device was called a cord. It never succeeded as a commercial product and went off the market. This was 20 years ago or so. But the particular problem that Mike set out to solve as a part of his dissertation research in my lab was a material inspection technology associated with the heating element in these devices. So the heating element is small and it's very thin, and it was made from a proprietary metal, iron aluminide, which was manufactured according to a powder metal process. That means you start out with a hopper, and in the hopper is the iron aluminide particles in an organic binder. Comes out of the hopper, is squeezed into a roller, and then goes down a conveyor belt where there's sequential squeezing and heating. It's never melted. It's think of it as a sintering kind of process. But you come out the other end of the process with a very thin metal that then can be stamped into the small shape that gives the heating elements. Okay? The technical issue that Mike set out to solve was how to minimize the scrap in the final part of the material by inspecting the very early stage green sheet for imperfections, changes in density, changes in thickness. In the green state, the material is so fragile that if you just rubbed it like that, that would end up with a crack at the far end of the process, and the material can't be melted down and recycled, so it just has to be thrown away. And as they were getting ready to go to market with the Accord device, they were having a problem with this heating element, and far too large a fraction of the material was coming out as scrap. So Mike's employer had this technical issue they needed to have solved. There was enough scientific interest and richness in the problem that it worked out really well for Mike's dissertation project, and in order to develop a non-contact, non-invasive inspection technology that could be used in the factory where the material was being made by a specialty chemical or specialty materials company in Connecticut. And the idea is that if you can identify the material variations that are happening early on, you then can provide feedback to the process to adjust the rollers or vibrate the hopper or various things like that. So that was the problem that was stated. And so we very quickly figured out that we were going to use infrared thermography in order to do the inspection. So infrared thermography, you use flash lamps to put down a burst of heat, and then an infrared camera sees the temperature variations on the surface as the heat goes into it and then comes back out. And then mathematical models of the heat transfer allow us to infer what's happening inside the material based on the thermographic imagery. And so the first thing that we had to do was sort of bracket the problem. And so we got access to the thermography laboratories of our colleagues at NASA Langley Research Center here. So Mike could get some preliminary data to figure out what was the right kind of inspection system to build. Once we had done that, Mike whipped out his corporate American Express card and purchased an infrared camera system that cost as much as my house. It was a really impressive system back in the day. Radiance HS was the name of it, and it had the ability to capture an enormous amount of data very fast, and that then allowed us to capture the snapshots in time of the heat flow in order to compare with our models of the heat transfer in order to figure out what variations in thickness or material density or things like that showed up as features in the images, and then understand what was going to happen throughout the process in order to figure out which imperfections in the green sheet were going to end up as cracks in the finished material. And so Mike put together a system in the laboratory with a couple of flash lamps and the Radiance HS infrared camera and a mock-up of the conveyor belt, and the camera so fast that any motion of the conveyor belt didn't matter, so we could set it up in the laboratory as a static measurement. And then Mike took a rather large amount of material back and forth to the factory in Connecticut to sequentially run the material through the process and keep track of what was where, even as it sort of got rolled out like pie crust dough or something, so that we could figure out where flaws showed up at the back end, and then backtrack in the early images to see what image features gave us those flaws at the end. Again, this is a machine learning play, although we wouldn't have known to call it that back in the early days. And so what we were doing was developing the training set to do machine learning, and it worked really well. We figured out what variations in the material properties of the very thin green sheet mattered. We backed up our analysis with heat transfer models, including models of the composite material of the iron aluminide particles in the organic binder, and wrote up the procedure and process in a way that resulted in a patent. And Mike finished his dissertation, went back to work, and his first job when he got back to work was to go about implementing this inspection system in the factory. And so he had to put out bids to get a system that could work in a factory environment as opposed to a research laboratory. And he got part of the way down that process, but then he figured out contractually that the supplier of the material, their contract told them that they got paid based on the amount of material that they produced, not the amount of good material. And so they had no particular incentive to improve their process. And before that could all get resolved, the test marketing seemed to fail, and the project just sort of died. After quite a lot of money, the actual amount of money that was spent on this, I wouldn't say, but it's large. There was a lot of money spent trying to develop safer cigarettes, and ironically that this was being done before the cigarette companies had officially acknowledged under oath that yes, they know that smoking is bad for you and nicotine is addictive. And so there's a new version of this sort of technology, the smoke.burn. It's heat not burn, and they're available for sale in some countries. I'm not sure which countries. You also, of course, can go to most stores and purchase old-fashioned analog cigarettes. You also, if you're old enough, can purchase the vaping devices. The nicotine is an addictive chemical. If you're not addicted to it already, don't start. You'll be sorry. We've known this since the 1930s. I'm Professor Mark Hinders, Applied Science Department at William & Mary, as.wm.edu.